Okay, good morning, everyone. Welcome to today's webinar. I'm Paola Maio from the European Heat Pump Association. I'm a EU project officer and also communication and dissemination leader of the Push to Heat project. Today's event is indeed organized in the framework of the Push to Heat project and is also part of the European Heat Pump Association Heat Peak webinar series. Through this webinar, we would like to really share real-world performance data and business case related to the implementation of heat pump technologies in the industrial site, specifically in the paper and pulp sector. So we will explore the engineering behind this solution, the integration challenges that have been faced, and of course, the expected impact and the results achieved so far. So before we begin, let me say just a few words about the Push to Heat project for those who may not be familiar with it yet. Push to Heat is a European project funded under the Horizon Europe program, and its objective is to demonstrate the implementation of 4 heat pump technologies for process steam generation while addressing the technical, economic, and regulatory barriers. At the same time, the project is developing innovative business models to penetrate the market. We are now entering the 4th year of the project, and through today's presentation, my colleagues will guide you through the latest advancement and key milestones achieved so far, with a particular focus, of course, on the work carried in the paper demonstration site. So we can have a quick look at today's agenda. We will start with an overview of the latest developments and policy updates relevant to the industrial heat pump sector, presented by Josephine Besseler, Policy Director at EHPA. And then we will move to the first presentation of the session from the Push to Heat project. Cordin Arpagaus from the University of Applied Science of Western Switzerland will present the results of a study on market opportunities and product market fit for high temperature heat pumps, together with a tool designed to help improve the competitiveness in the market. Next, Abdel Hassan from the University of Valencia will present the technical and environmental analysis of integrating high temperature heat pumps into an Italian paper mill, which is the Push to Heat demonstration site 2. And this will be followed by Laura Alonso, senior researcher at Tecnalia, who will showcase the integration of a different heat pump technology within the same paper mill in Italy, focusing on the demonstration site 3 of Push to Heat. We will move then to another success story on integration of the largest scale heat pump in a paper mill in Finland, presented by Rob Caltieri, Senior Sales and Business Development at Turboden. And finally, we will close the webinar with the usual Q&A session. Few housekeeping rules about the webinar. So in these Teams features, participants cannot turn the camera or microphone on. So we suggest to write in the chat every question you might have during the session. You can also tag directly the speaker so that they can answer directly in the chat. And then we will address this question in the latest part of the session. If you have to leave early, don't worry, we will send the slides as well as the recording of the session to all the attendees at the end of the webinar. So I think we can start, and I can give the floor to Josephine Besseler, Policy Director, that will give us a few updates relevant to the industrial heat pump sector. Please, Josephine.
Thank you, Paola. And good morning, everyone, also from my side. Yes, I have to take control indeed, important. Okay, how do I change slides just like this? Yes, okay, so good morning, everyone. Indeed, as Paola indicated, this webinar is part of the Heat Peak webinar series that we are organizing as EHPA and which is supported by Turboden. So the aim of this Heat Peak webinar series is to really show how industrial and district heating solutions are being implemented. So why do we do this? It's because to have the biggest impact on the rollout of industrial heat pumps, it is by showing peer-to-peer examples and by showing actually to end users what is already being in place and results of projects that are being implemented and demonstrated. So that is why we set up this webinar series. And thanks to the support of Turboden, we also can really target the specific end users to join these webinars. So we can create specific LinkedIn ads, make publicity in specific end user magazines. So we really reach as many as possible end users to see what is potential or what is possible in their sector and what has already been implemented. So we do these webinars as much as possible also by integrating, as I said, concrete cases, also by using the different project results and the work that is ongoing in the project, but also many other topics or many requests that we receive also, for example, from end users. So we're working on several upcoming topics. So on the 18th of June, we will have another webinar on industrial heat pumps in the dairy sector. And then on the 25th of June on industrial heat pumps and organic ranking cycles. And then we are working on upcoming webinars, for example, one on industrial heat pumps in the chemical sector and on financing for industrial heat pumps. So much more to come. Keep an eye on our website to stay tuned on this. So why are we doing this? This also frames in a bigger policy context. As you can see here, last month, the European Commission published the Accelerate EU document. It's the Commission's reaction to the current Middle East war and how we should improve our energy security. And this document really, for the first time, puts electrification as a central EU priority to move to more energy security. The focus in the document is also very much on electricity to gas price ratio, so to improve that and to have a better rollout of electrification. It encourages member states to take action to improve the electricity to gas price ratio, and it's also looking itself, so the EU, at EU level on which action they can take. They also mention very clearly the importance of good financial support mechanisms for heat pumps, and there's a lot of focus also on heat pumps for industry, district heating, and system flexibility. They also published a catalog with national best practices for electrification, for example, and there Finland is mentioned also for its good electricity taxation rates for electrified heating. So this also fits very well with the case that we will have presented at the end by Turboden in Finland. So next to that, also at EU level, we have the Innovation Fund's heat auction. There was a first one that was launched in December 2025 and closed in February 2026. So it's an auction for subsidies for industrial heat pumps. And 2 days ago, the European Commission announced that a second round of this auction will take place later this year. So that's very good news for our sector. So you can already take that into account and wherever possible start preparing to participate in that auction. There will be a budget of 1 billion euros, and currently the Commission is finalizing the draft terms and conditions and will publish those in the next days. And yesterday EHPA had a meeting with its members and with DG Klima, DG Ener and CINEA to really discuss also this auction and how to further improve the draft terms and conditions. So also that is upcoming. So indeed, we have these EU level actions, but then we need to reach out to end users to make them aware of what is already possible. And at EHPA, we are doing that also with CEPI, so the Paper and Pulp Sector Organization. We have a collaboration already for quite some years. We published some papers on what a blueprint process in the paper and pulp sector looks like and how a heat pump could fit into that, and also what are the different potential solutions. So you can find these on our website. And this collaboration actually inspired the Commission also to fund a number of additional projects looking into how end user sectors can further be informed and collaborate with the heat pump sector and other sectors to further decarbonize and electrify. So here you can see the projects on industrial heat pumps and district heating heat pumps that EHPA is currently working on. So the 3 without the logo are very new ones that are starting in the next months. And then the 3 with the red circles are the ones that are specifically focusing on pulp and paper. So very interesting for this audience also today. So you can find more info on our website. Yeah, and the others also focus on other sectors like chemicals, food and drink, dairy, and also cross-sectoral topics. There's one project that I want to highlight a little bit more because it recently started, and it's the Green Spire project. You can see here. So this project really focuses on green strategies and partnerships for industrial renewable heat. So it looks at how, for example, in an industrial park or a port, how the different companies can really collaborate closer to share their sources and their renewable heat technologies to have the optimal way to reduce their CO2 emissions. So it looks at 6 demo cases or pilot sites in Belgium, Denmark, and Spain and Greece. And it focuses on different technologies such as solar thermal, high temperature heat pumps, thermal storage, and waste heat recovery. So stay tuned also for this one. And now I hand back to Paula to focus on the paper and pulp sector.
Thank you, Josephine, for this overview. I think we can go now to the first session of the webinar from the Push to It project. I'm really happy to present Cordin Arpagaus, which is a senior researcher at the Eastern Switzerland University of Applied Science. They will give us a presentation on the market opportunity and product market fit for the high temperature heat pumps. Please, Cordin, whenever you're ready, the floor is yours.
Thank you, Paula. I hope you can hear me well. Yes, okay. So my name is Cordin Arpagaus. I'm from the Eastern Switzerland University of Applied Science. I'm gonna talk about market opportunity and product market fit. So we developed in Push to Heat a tool that I would like to present. So it was a collaboration from OST, from our university, with the Institute of Energy Systems and the Institute of Strategy and Marketing. So I would like to present this so-called business model co-pilot tool. It's a framework for evaluation of product market fit developed in Push to Heat. So what is the motivation from a heat pump provider? So first they have to sell heat pumps. So the sales funnel is very important, and which lead to follow and which should be prioritized first. So there are many leads or customers. They have to be qualified. Then some offers are sent to these customers, maybe some letters of intent or memorandum of understanding, then negotiations, and at the end, hopefully a sale. And this conversion rate should be improved or increased. So that would be a major goal. So what is the focus? The focus is to find these most promising use cases and have the business model and the sales process dedicated to this goal. And the keyword is matchmaking. So matchmaking of the product propositions and the customer needs, so the buying criteria. We have this so-called competitive advantages and the key success factors. So the research question is, which high temperature heat pump technology or industrial scale heat pump technology matches the customer needs and the market demand best? And here we have the key success factors. We have an internal view from the company and an external view. So what do the customers really want? And from internal view, also what are the competitors? They need to survive this competitor situation. Maybe there are some others which provide a similar technology. And yeah, to find out what are really the competitive advantages and have this product market fit. So in Push to Heat, we had the following approach to derive this business model co-pilot tool. First, we did a lot of interviews with experts, so practitioners and also experts from science and also literature research, desk research. From that, there was this analysis and then a qualitative result. And the result is an Excel prototype, so a tool which contains these key success factors and competitive advantages. So several criteria that has to be quantified. And at the end, then this test this tool was then tested within the push-to-heat partners, especially the heat pump providers, and this work is still a little bit ongoing. So what is it now? So it's a pre-sales tool, a scoring tool for the product market fit. So from an inquiry to a fit score. So we are on the left side, on the one side, we have the market appeal. So the key success factors so that drive these customers. So the driving parameters and also pain relievers, so we call it. And on the other side, we have the heat pump provider, which is actually the user of this tool, and they provide a competitive advantage. And then we have this matching of the technology and the market, and we weight these different factors and come up with a fit score and lead priority. That's the final goal. So on the left, we have the market factors, the criteria. This can be market scale. So what is the potential of the market? What are the emissions that can be reduced? What are the costs of carbon? And what are the, let's say, the decarbonization goals? So we have the waste heat as a parameter from the market, and the process fit. So is the application where this heat pump would be integrated suitable for a heat pump? We have different factors here. And then on the other side, we have more technology-related factors like the efficiency of this heat pump, the costs, capabilities for temperature, then also have this technology be integrated in other cases, so replication cases, and so on. So we need factors like trust, service, delivery strength. So this is common sense research, I would say. It's not so exact research. So there's always discussion and different opinions on these different factors. But at the end of the day, salespeople need to quantify or come up to a certain value number. So now I go a little bit into more detail. Josephine told about the price ratio. That is very important to accelerate heat pump adoption in the market. And this is very much related to the COP, or the efficiency of the heat pump. Here we have a fit curve. This has been presented or published some years ago, but it's still valid. This fit curve is representative for many industrial heat pumps. And it's the curve showing the COP as a function of the temperature lift. So the temperature lift between the heat source and the heat sink in the application. And this is about almost a 50% Carnot efficiency. So with this fit curve, we can connect the efficiency of the heat pump to the application, to the temperature lift. And now to find a business case, we have this very simple formula. We have the price ratio of electricity to gas. So we compare, let's say, an electrified heat pump, a compressor, vapor compression heat pump with a gas boiler. And the gas boiler is typically already installed at the industrial site. So it would be like a retrofit situation. And then we have the efficiency of the gas boiler. So the price ratio is very much depending on the country, on the local situation of this particular industrial company. They have some contracts of energy supplier for the energy supply. So this is known. This is given. And the gas boiler efficiency, 90%, let's say, is also somehow given. And the COP has to be higher than that. That's very simple formula. And we have now this relation to the temperature lift to the application. So we know this fit formula from industrial heat pumps. We know it and can now link all that to this application. And so we have three factors: this price ratio, the COP, and the temperature lift. Now in Europe, we have different price ratios in the different countries for industrial companies. This can vary a bit, but here is more actual data, and we can see, okay, Scandinavian countries, Sweden, they're 1.2, so very low price ratio. So market attractiveness for electrified technologies is high. But in the UK, that's darker there, the price ratio is high, so very cheap gas prices. Now we can convert this now with the fit function to an economic COP. And this is now shown here in this map. And now the third map is the temperature lift. So as an example, in Switzerland, you can see it, the numbers are a little bit small there, but the price ratio in Switzerland is about 2.4. This gives an economic COP of 2.2. So the COP has to be higher than 2.2, and this is related to the temperature lift of 89 Kelvin. So now if we have an application with waste heat of 50 degree and add 89 degree, so let's say 90, then we come to 140. So 140 degree heat sink would be still an economic case with 50 degree waste heat in Switzerland. So very simply put, but I think this is important also for policymakers, that they understand, let's say, the very basic economic point for heat pumps. Okay, so that's it. So the product market fit depends then very much on the technical features. And for a heat pump, which is driven by a compressor, the compressor technology is very much deciding on that. And here we did discussions and workshops and tried to come up with a spider diagram for different compressor technologies. So we have different criteria to judge, let's say, which compressor technology fits better in what conditions. For example, screw compressors are flexible in refrigerants, for example. Reaction time to volatile sources is high, and so on. When we overlay a piston compressor, this is probably more suited when the loads are varying often, so it's more efficient with variation of part load operation. The pressure ratios can also be higher with the piston compressors. Okay, it's always discussion here, but it just should illustrate that the thinking steps are to think which technology, which compressor technology fits best to the application, what are the attributes. The turbo compressors, we will see later, have the advantage of high capacity, so they can reach several 10 of megawatt heating capacity, for example. And so these technical performance factors are the potential value drivers, and this gives then customer value. So this has to be done. So compressor technology is important. We have in push to heat the company SPH, and they have the piston compressors here in the paper factory in the Felix Schoeller group. And what is important is that this compressor technology is very flexible. So here we can see the time scales for startup or to reach full load operation. Look at the red columns there. So if the heat pump is hot and the oil in the compressor is preheated and the refrigerant circuit is already warm, and so it takes only a few minutes to full load, maybe 10 minutes or 3 minutes. So it's a very flexible technology with this piston compressor technology, and this offers a technical advantage. For example, the shutdown is in 5 minutes, emergency stop in a few seconds, and yes, it can start several times per day. So this is just an example of the thinking steps behind this product market fit tool. Another parameter is, for example, the refrigerant, and here we can see that the future looks like to go into natural refrigerants, and especially for the industrial scale or industrial application, hydrocarbons. which offer high temperature applications. Then we have ammonia, CO2, water, and so on, and also HFOs. So if the heat pump that would be interesting for the customer offers natural refrigerants, that an additional competitive advantage. And another important point is then the load profile. So what is the capacity or the temperature need over the day at the company? And here we have some handwritten drawings, but we can imagine a company with a very volatile production, a two-shift operation, start at 6 o'clock in the morning, and then we have the production. And here on the other side, we have a more continuous process, a company that has always need of process heat. And we also see the waste heat sources that are needed to be accessed with the heat pump. Another profile could look like that, or here we have an example of a district heat network, which starts also in the morning to provide the heat, and then over the day decreases towards the end. So this is arbitrary data, but the thinking step is here to look at the profile and to now fit the heat pump technology to that demand. Another aspect is from the sales people, where do they have their customers? And from surveys, we clearly see food and beverage is a very interesting market for the heat pumps, and the chemical sector, paper sector that we are talking today, and others. So that's another market research. And another aspect is the waste heat. So here we have a table that we developed also in the Push to Heat project that shows the waste heat recovery factor by the sector and temperature levels. It's a lot of this slide, but we can see that, for example, in Spain, we have 62 terawatt hours of waste heat, and this can then be distributed in different temperature levels. And we see below 100-degree waste heat, the lowest line there, we see high potential pulp and paper. In the middle of the slide, 75%. So it seems that this sector offers high waste heat recovery potential, and also at the temperature level that is suitable for heat pumps. So this waste heat recovery analysis is also part of the game to find a good product market fit. And there are many other factors as well. Also the business model. Here we have a survey result that shows that most customers would like to buy or to purchase the heat pump and own the heat pump by themselves, which means for a heat pump provider that they would sell this. So this means they need salespeople, installation people to really install then the heat pump at the site. Energy as a service, heat as a service are also seen as possible business models. So these business models are also important. So to sum up a little bit, we have from the product point of view several criteria. We need to do the analysis and then weight them. And on the other side, we have the market that has also criteria that has to be quantified. We have then this product market fit, and then this provides then information for the sales funnel, for the positioning, for the revenue model, and the business model fit. So the key takeaway from this talk, I tried to show you, let's say, this business model co-pilot tool that we develop in Push to Heat. It may be useful for identification of leads, also for strategic analysis, to analyze markets and technologies. It shows the competitive advantages and also shows an outside-in perspective. I would say flexibility of the heat pump technology is very key. It offers many application potentials. And last but not least, keep this, let's say, very simple formula in mind to link the price ratio, the COP, and the application with the temperature lift. So thanks a lot. Push to Heat mentioned several times. We have here the links to go to the website, LinkedIn, and YouTube.
Thank you so much, Cordin, for this presentation. And for the audience, if you already have some questions, you can put them in the chat so that we can move on with the other presentation and we can address them later in the Q&A session. So yes, I suggest to move on with the next speaker, that is Abdel Hassan, which is an adjunct professor at the Technical University of Valencia. He has been working in the field of HVAC and refrigeration equipment, and recently he has been focusing on integrating high temperature heat pumps into the industry and thermal storage system through active participation in European projects such as Chester and Push to Heat. Thank you, Abdel, for being with us. And whenever you're ready, take control of the presentation.
Okay. Thank you very much, Paola, for this great presentation. So I am Abdurrahman Hassan, postdoctoral fellow and adjunct professor in Technical University of Valencia. And I'm here to present some results regarding the techno-economic analysis and environmental analysis of integrating an industrial high temperature heat pump in pulp and paper industry within the Push to Heat project. As introduction, DeBoer et al. In 2020, in their white paper, they indicated that the total energy demand in European Union is 2,950 terawatt hour per year. 66% of this heat demand is process heating, or the total energy demand is process heating. The majority of this process heating is for temperature higher than 500 degrees. And as we can see, there is also 96% in the range between 100 to 200 and 11% in the range below 100 degrees. The majority of this heat process heating is covered by fossil fuels. The majority of this heat, especially gas, natural gas, which represents 36% of non-renewable energy sources. Increased energy efficiency through the recovery and upgrade of waste heat is the first step towards decarbonization in the industrial sector. For example, high heat pump technologies nowadays could potentially deliver 730 terawatt hour per year, which represent 37% this range of temperatures between 100 to 200 and below 100 degrees. Based on this, or in this context, we can say that the Push to Heat projects or project aims at pushing forward the market potential and business models of heat upgrade technologies by full-scale demonstration of heat upgrade systems in relevant industrial sectors, with supply temperature in the range of between 90 and 160. This figure shows like the partners in the project or Push to Heat project, which relate to different European countries. In Spain, as you can see, we have Tecnalia, we have Technical University of Valencia, Cardiff. In Belgium, we have EHPA, Q-Bench, which is a manufacturer for chemical heat transformer, Vito. Also, we have in Germany, Fletcher Group, which is a manufacturer of pulp and paper, SPH, manufacturer of high temperature heat pump, Nova, manufacturer of absorption heat transformer, Technical University of Berlin and Fraunhofer. In Switzerland, we have Host University, Cordin and his team. And in Italy, we have Politecnico Milano, and we have Ono and CDG, which is a manufacturer of pulp and paper. Within the Push to Heat project, we have different demo sites. Demo 1, which is in Fletcher Group. In this demo site, we will test a cascade high temperature heat pump produced by SPH. In Belgium, there is test site in Borealis, which is a chemical company. In this, we will test chemical heat transformer by Q-Bench. And in Italy, there is Cartiere di Guarcino, or CDG, We have 2 demo sites. Demo 2, in which we will test the temperature heat pump plus mechanical vapor compression technology by Bono, and Demo 3, which is absorption heat transformer coupled with a steam ejector by BS Nova and in collaboration with Technale. And I think this is the next presentation by Laura. In this presentation, I will focus in Demo 2, which is the testing of high temperature heat pump plus mechanical vapor compression. So as a fast overview of task 5.2, which we are the leader of this task, UBV. In this task, we will focus on the potential application of the assist heat upgrade technologies in different industrial sectors. So we have analyzed 13 industrial cases related to 6 different sectors, and we have analyzed the feasibility of integrating 3 technologies: absorption heat transformer, chemical heat transformer, and high temperature heat pump. So one of these cases is the demo site 2 in CDG. So I will start by what is the waste heat availability of this demo site. So the waste heat will be extracted from the water cooling circuit of the combined heat and power plant CDG, as you can see here in this figure. So it contains primary cooling loop, which cools 3 fuel engines of 6.8 megawatt electricity of each one. As you can see, the outlet temperature, water temperature will be, or it's in the range of 94 degrees, and the return temperature should be in the range of 72 degrees. This heat is rejected to a secondary cooling loop through these 3 pressed plate heat exchanger. Each one has 2 megawatt capacity. If the temperature is higher than 72 here, we can use also dry coolers, as you can see, dry cooler 1 to dry cooler 3 to reduce further the temperature before the water enters again to the these engines. In the secondary loop, basically the rejected heat or the extracted heat is used to heat the combustion air here in these heaters, the air that used later in the combustion process. Each one has 1.5 megawatt capacity, and the rest will go to district heating of the CDG at 90 degrees. And after making energy balances and trying to extract more heat from this system, we have managed to have 1.3 megawatt waste heat, extra waste heat, 0.6 megawatt for high temperature heat pump, and 7.7 megawatt for the absorption heat transformer. This heat is available during 7,000 hours per year. So based on this, we put this concept of integrating high temperature heat pump in CTG, as you can see in this concept diagram. So we will recover heat from 90 degrees water. We will recover approximately 600 kilowatts at the high temperature heat pump, which will consume 143 electricity. It will produce saturated steam at 1.7 bar A. Next, we will use the mechanical vapor compression technology to increase the pressure to 6.5 bar A. Here you can see the details of nominal point operation. You can see the source side, the inlet temperature will be 90 degrees from the cooling circuit. We will extract 600 kilowatts. In the sink side, we will use the water from the aerator at 105 to increase its temperature, preheating it 115, and we will produce saturated steam at 115 at 0.4, which corresponds to 1.7 bar A. Then we will use mechanical vapor compression system to increase the pressure to 0.6, which will have a pressure of 6.5. Here we will inject in this compressor, we will inject water to cool down the compressor and also ensure that the outlet at 0.6 is wet vapor or saturated vapor. Here in 0.7, we will extract any water droplets from the outlet, and in 0.8 is steam, saturated steam, which is integrated to the steam collector header at 6.7 bar. Here you can see 3D scheme of the system. Here we have the high temperature heat pump, which is a mechanical vapor compression system, which is basically a screw compressor technology. The heat pump also uses a screw compressor. Based on this nominal point operation and the data from the manufacturers, we have tried to estimate, try to figure out where we will integrate our system. The first scenario was integrating this system in the primary cycle here with one of these motors. And this solution was infeasible due to many challenges like contamination of the primary loop, fuel of flue gases, or failure or maintenance of this engine. The second scenario was to integrate it with the 3 engines in parallel, and also this is a complicated solution, especially from the point of view of control and cost. And the final scenario, which we are doing now, is scenario 3, integrating this system in the secondary loop system, as you can see, parallel with district heating of CDG, which is simple implement and simple in control. So based on this, we have also developed an ES tool and is validated with nominal conditions. This tool will help us later to generate performance maps that will be used in the dynamic model to estimate the system performance or dynamic system performance. If you need to know more data regarding this, how we are model these type of systems, you can refer to our published paper 2002 in Gustav Lorentz conference in Norway. And finally, you can see here the techno-economic and environmental analysis at the nominal point. We compared our system with a gas boiler that has a fixed heating capacity of 833 kilowatts. So these are the fixed parameters during the study. We have gas boiler with specific capex of 100 and efficiency of 90%. The estimated specific capex of the system is 900 euros per kilowatt thermal. We use the installation integration factor of 1.5 to take into account the installation, integration, commissioning, etc. We have operating and maintenance percentage 4% from the capex. Electricity cost and gas cost are 148 for electricity euros per megawatt hour and 53 for the gas. And we have CO2 emission intensity for gas and for electricity. We take this value from Statista website 2025 in Italy is like average value. We have CO2 emission tax of 95 euros per ton CO2. Annual working condition, as I have mentioned, 7,000 hours. And in the other side, the gas boiler will work almost during the year, 8,424 hours per year. The expected lifetime is 20 years. Inflation rate 3 and discounted rate is 5. So based on this data, you can see here in the radar diagram the comparison between our system in red, proposed system, high temperature heat pump plus mechanical vapor compression, and gas boiler as a backup boiler to cover the deficit in the annual working hours. So you can see that there is a huge difference in capex. It's expected. However, the levelized cost of heat, you can see they are quite similar, 97 euros per megawatt hours in case of in the proposed system, and 98 for the gas boiler. We have a big gap in the capex, but we have also saving 0.1 million euros per year. The heat demand coverage is 83%, and this is due to the deficit in the working hours, mainly of this. Regarding CO2 emissions, we have a significant emission saving, which is 817 tons CO2 per year compared with the gas boiler. And we have levelized cost of CO2 abatement of minus 12 euros per ton CO2. This parameter is used to estimate the cost that we should pay, or the money or the amount of euros that we should pay to avoid CO2 emissions. Negative values means that we are in a win-win situation. So we are reducing CO2, and in the same time, we have savings. Okay? And finally, primary energy efficiency. The heat pump has a significant primary energy efficiency compared with gas boiler. This means that the heat pump in this scenario can produce an amount of heat equals to 1.3 almost times the primary energy consumption. Okay. More details about the calculation methodology used in this study, you can refer to this paper, which is published recently by the partners in Work Package 5 in Push-to-Heat project. And finally, as a conclusion, this study shows the feasibility of designing and integration of a high-temperature heat pump plus mechanical vapor compression system in paper plant that could work between 90 degrees as a source and sink till 162 degrees. Under nominal working conditions, it can work up to 7,000 hours, delivering total heat of 5.8 gigawatt hour per year, consuming 2 gigawatt hour per year electricity with COP of the system of 2.85. And I don't know why it's like this, but this should be a second law efficiency of 49%. The technical economy and environmental analysis of the proposed system shows an OPEX saving, CO2 emission saving, levelized cost of heating, and primary energy efficiency of 0.1 million euros per year, 817 tons CO2 per year, 97 euros per megawatt hour, and 125% respectively compared with the gas boiler. Finally, the expected payback period is 15 years. It's long period, but this contributes to the deficit in waste heat and the high also integration cost of such technology in the industry. So that is my presentation, and thank you for your attention.
Thank you so much, Abdel, for this presentation and the insight related to demo 2. And to link to the next presentation, as I mentioned before, in this demo site, CDG, we have 2 different technologies. And that's the case of the next presentation led by Laura that will introduce us to demo 3. Laura Alonso is a chemical engineer specialized in energy system and fluid thermodynamics. With more than 10 years of experience working at Tecnalia in the Efficient Thermal Energy System Research Group, her work involves the development of R&D projects related to energy efficiency and thermal energy system and equipment, particularly in the advancement of heat upgrade technologies and system for industrial decarbonization. Laura, whenever you're ready, you can take control.
Thank you very much, Paola. Okay, I think I have the control now.
Yes.
Okay. Yeah. Okay. Good morning, all. Okay, this is the start of my presentation. I will speaking about the steam generation using an absorption heat transformer. As Paola said, this is one of the demonstrators of push-to-heat project, and I will show all the process of design, integration, and the first results we had during the commissioning phase of the installation. Okay. Well, previously all the demo sites of a push-to-heat project have been introduced by the previous presenter, by Abdel, but I wanted to show in this slide again the 4 different technologies in order to focus on the differences we have between the technologies, because in the first 2 demos, demo 1 and demo 2, we talk about compression heat pumps, which are electrically driven heat pumps. And normally this technology has 2 different temperature levels. So we have the waste heat input at a medium temperature level. And thanks to an electricity consumption in the compressor, we have the useful heat or the upgraded heat at a higher temperature level. But on the other hand, we have also thermally driven heat pumps, and in the push-to-heat project, we have 2 different technologies that fall under this category: the absorption heat transformer and the thermochemical heat transformer. In the inside, they work differently, but if we look at the outside conditions, the functioning or the basics would be very similar. So in this case, we have 3 different temperature levels. The waste heat comes at a medium temperature level, and approximately half of the heat that is coming at a medium temperature level can be upgraded at a higher temperature level, and the rest of the heat needs to be rejected or dissipated at a lower temperature level. And when you compare this with the compression heat pumps, you have a minor electricity consumption, just a little bit of electricity consumption for internal pumping in the system. because this is mainly thermally driven by the waste heat. And now I will focus on demo 3. Okay, the installation number 3 in push-to-heat project is located in Quartiere di Guarcino paper mill, the same as the one that we have seen in Abdel's presentation. So demo 2 and demo 3 are together in the same plant. We are leading this demonstration site from Tecnalia and collaborating very closely with our technology partner, the Technical University of Berlin. The manufacturer of the absorption heat transformer is BS Nova, the plant owner, the Quartiere di Guarcino, and the engineering company and integrator of the whole system is Canon Bono. Okay, here we have a representation of how the system is integrated into the plant. And as we mentioned before, the two demo sites, demo 2 and demo 3, will be installed in the same plant and also share the same waste heat. So the same as before, we are taking waste heat at around 85-90 degrees from the cooling water of the cogeneration plant, as Abdel perfectly explained. And this is coming to the heat transformer. And in the heat transformer, we upgrade heat at a higher temperature level, around 145 degrees, and we provide hot water. But what is needed in the plant is steam. So we produce this steam externally to the system in a flushing tank, in which we produce low pressure level at around 3.3 bar. And then we combine this system with a thermocompressor, which uses also high pressure steam, which is available in the plant. And this high pressure steam is mixing with the low pressure steam we produce. And so we get the final steam at 6.5 bar, which is the pressure level needed in the process. And this is injected to the medium pressure steam header in the plant. Talking about some KPIs, when we talk about the efficiency of this system, normally in thermally driven heat pumps, we will talk about the thermal COP, and this means the amount, the power of upgraded heat at higher temperature level divided by the amount of, or the power of waste heat coming into the system. And this value is around 0.48. And when we talk about the electrical COP, this is much higher because, as I said before, the electricity consumption of the system is very low. The electrical COP would be even higher for only the EHC, but when we combine this with the external system for producing the steam, it's a bit lower, around 35. Okay, and with the estimated operating hours per year of 7,000, we will have this primary energy savings of around 2,800 megawatt hour per year and savings of around 500 tons of CO2 per year. Okay, here again, a representation of the 3 different temperature levels of the absorption heat transformer, because this is a quite different technology from if you compare it with the compression heat pumps. So we introduce the waste heat in the evaporator and in the generator. In this case, we are introducing the waste heat in series in these elements. We upgrade heat in the absorber, and we reject heat at a lower temperature in the condenser. The cycle is uses a mixture of water and lithium bromide, and we have different pressure and temperature levels, and the useful effect comes from the absorption of the lithium bromide, of the water in the lithium bromide mixture, because this process is exothermic, so we have the useful effect of the upgrading heat in the absorber. Okay, here are a presentation of how the system is integrated with the different streams connecting with the plant. So this is the waste heat recovery circuit, which Abdel explained before. So this will share the waste heat to the compression heat pump and to the heat transformer. In the heat transformer, we take the waste heat in the evaporator and generator in series. Then in the condenser, we are ejecting at a low temperature level at around between 15, 20 degrees. And we upgrade the heat in a water stream at around 145 degrees. Then this water stream goes to the steam generation module. The steam generation module would be more or less this part. And so part of the water that comes into the flash tank, only a small part gets revaporized because it's expanded, and we get the low pressure steam. Then this is mixed with high pressure steam in the thermocompressor, and finally we get the medium pressure steam. As part of the water is revaporized, we need to fill with new water, and this is coming from the feed water line from the deaerator, as in case of the demonstrator number 2 at around 105 degrees. Okay, now focusing a little bit more closer on the steam generation part. We have the first step of the steam generation is the flash tank. So here we have a representation in the temperature enthalpy diagram of how is this process. No, we have the hot water that we got from upgraded heat from the absorber, and this water comes into the flash tank expanding, and so this expansion makes that we have a two water steam mixture. So we got only a small part corresponding to the steam quality that we have in this mixture. Only a small part is revaporized and comes out as a saturated steam out of the flash tank, and the other part comes out as a condensate and goes back again to the heat transformer. The higher is this temperature and pressure difference, the higher would be the amount of steam produced, or the percentage of revaporized steam. Okay, then we have the thermocompressor, the second step for upgrading the pressure that we get from the flash tank, because we need higher pressure in the process. So the thermocompressor uses the potential energy of the motive steam, which is the high pressure steam that comes at around 14.5 bar absolute from the boiler of the plant. And this is converted into kinetic energy in the steam nozzle, and this makes a pressure drop and a suction effect. So the motive steam is suctioning the low pressure steam, and then the mixture expands in the diffuser, and we get the medium pressure steam at the outlet of the thermocompressor. And here we can see for the estimated value of 540 kilogram per hour that we will get in the flash tank, in these conditions, in this proportion of pressures that comes into the thermocompressor, we would need around 2,000 kilogram per hour of high pressure steam. So at the end, we will have more or less 2,500 of kilogram per hour coming out of the thermocompressor. Okay, how is the status of the demonstrator? What phases have been done to fulfill this installation? Well, the heat transformer and the steam generation module were manufactured and delivered to the plant last year. All the installation was completed last year, and the commissioning activities were held at the last quarter of 2025. And also, after making all the checks and making sure that the system was working well, we performed the first performance tests at the end of the year. Nowadays, we are developing the last checks in order to put the system running in continuous operation, and 1 year of monitoring period is planned for this demonstrator and also for the rest of the demonstrators in the push-to-heat project. Here are some pictures which can be interesting for the EHT construction. This is the EHT bundles can be seen, the whole assembly, and here insulated in the manufacturer's premises and ready for transportation. Here we have the moment of the arrival of the heat transformer to the Italian paper mill. So first, the EHT was placed outside the building, and a vacuum check was done because this system is working under vacuum. It's very important to maintain the vacuum. And then the EHT was placed into the building, and this was a big challenge because it was not easy to do that, and part of the roof had to be removed, and a big crane was used to place the system carefully inside the building. And this is how the whole system looks like when installed into the plant. So we have the EHT. At the left side, we can see the steam generation module. Only a small part can be seen here. And here are the pumps for the waste heat that comes into the system. Here in the right picture, we can see a little bit closer the steam generation module. And as you can see, we have two valves. So the valve on the top allows the steam to be rejected to the atmosphere, because the first tests have been done rejecting the produced steam to the atmosphere. And then when it was sure that everything was working fine, we used the other valve to conduct the produced steam to the medium pressure steam header in the plant. Okay, these pictures show the first time that the steam was produced. As I said before, the first trials were done rejecting the steam to the atmosphere, and this picture shows the first time, so the first steam produced by the unit. And as we were making the system run in different phases, on the first phase we only used the flash tank, so we tested it producing only low pressure steam. And then we used the whole system, so combining the low pressure steam produced with the thermocompressor and producing the whole amount of steam. And as you can see the difference, we produce much more steam when the thermocompressor is used. And then the next milestone was to introduce the produced steam into the medium pressure steam header, which was successfully done at the end of last year. And here we can see some graphs showing the different conditions we got in those trials. So we can see the three different pressures in the thermocompressor. The low pressure steam coming from the flash tank at around 2.3 bar G. The high pressure steam coming from the plant, and the medium pressure steam at around 5.5 bar G, which is the useful steam injected in this medium pressure steam header. And below we can see the different temperature levels of the heat transformer. So the waste heat coming at around 90 degrees, the upgraded heat at around 145 degrees, and then the dissipation stream at around 15 degrees. Okay, and this has been all. Thank you for your attention, and if you have any questions, I will be happy to answer. Thanks.
Thank you, Laura, for the presentation, for bringing us inside Demo 3. We can move forward to the last presentation of this session. We will have another case study and success story about the integration of heat pump inside a paper mill, which is now fully operational. And we will have Rocco Altieri from Turboden to showcase it to us. Rocco holds a master's degree in energy engineering with a strong background in thermodynamics and power generation. He has more than 10 years of experience in the field of energy efficiency with sales roles in the renewable energy and refrigeration sectors. His current mission is to play a part in fostering the electrification of it across Europe. Please, Rocco, whenever you're ready, the floor is yours.
Thank you, Paola, for this introduction. Hello, everybody. I will take the control. Okay, so I'm ready. Thanks again for being present in this webinar. I will be happy to conclude my intervention showing you what we did as Turboden in our largest heat pump installed so far. So I will present firstly our company for those who don't know us very well, let's say, and then I will focus on the project itself. Yeah, so Turboden as a company was founded in 1980 as a spin-off of Politecnico University of Milano. Since then, we position as a company for designing and supplying of energy efficiency solutions. The main business of the company was and is nowadays the design and supply of organic racking cycle power plants. But 5 years ago, approximately, the company decided to enlarge their portfolio in terms of energy efficiency solutions, adding industrial heat pumps. So since then, we developed internally the capabilities to design this kind of industrial plants, and thanks of being part of Mitsubishi Heavy Industries Group since 2013, we were able to develop already let's say a reliable solution for heat electrification in the industrial environment. As a company, since the beginning, Turboden, as of now, developed and supplied more than 470 plants around the world. 3 projects are from our business unit, so for heat electrification systems. I will talk about one of them later in this presentation. Turboden, as said at the beginning, as a company can propose quite a strong experience in designing plants for industrial purposes. We have in-depth knowledge of thermodynamic design, mechanical and electrical design, and also control logic for the system that can make us as strong solutions for industrial customers. We have the capability internally to design basically all the system, especially focusing on the turbo machinery. So both the turbines for power plants and the compressors for heat pumps are designed internally with the knowledge of our designing team, and also with the support of Mitsubishi Industries colleagues. In general, in a project, we are able to manage the first phase of engineering up to the commissioning of the plants and the after-sales activities. Both for utilities customers like multi-utilities, municipality companies around Europe, but also for industrial customers, including the process integration. In terms of thermodynamics, I wanted just to have a quick focus on what we propose in terms of refrigerants, because as Professor Arpagao said at the beginning, there are a number of possibilities here. And we, as a solution provider, we are pushing and proposing natural refrigerants based on hydrocarbons for our heat pumps. That is why the market is starting to require more and more this kind of solutions. And also from our knowledge, from our experience from power plants, we are very well, let's say, structured to design these units with this kind of working fluids. So we feel very confident that we can transmit this confidence also to final customers. In terms of portfolio, as a company, we can propose, as said, large heat pumps for industrial utilization, but also MVR systems. So basically, MVR can be considered as open cycle water heat pumps, where the condenser is the process, industrial process itself. In this case, we developed internally also the compressor technology for steam, starting from what we did already for our heat pumps. And by the end of this year, we will be able also to install our first steam compressor in an industrial customer in Italy. In terms of products, so we can have both heat pumps and steam compressor. On the heat pumps, I would like to give an additional information, because Two solutions are available, let's say. A first modular unit that we developed recently is able to provide from 5 to 15 megawatt thermal at the thermal user. This kind of solution is based on pre-engineering and pre-engineered heat pump, basically, where both the compressor and the heat exchanger, but in the entire system is pre-designed, let's say, and pre-assembled on skids on our in our premises. So in the end is a cheaper solution that can be easily installed inside the industrial facilities. On the other hand, we can also propose tailor-made heat pumps. That is our typical approach for large projects, so from 10 to 80 megawatts, so very large units. In this case, we could also leverage the possibility to implement a compressor supplied directly by our mother company, Mitsubishi Heavy Industries, that we propose for very large units, and it is a compressor derived by oil and gas industry, so it's very heavy duty machine. Third product, as mentioned before, is a steam compressor we are developing now. We will be able to install as a first of a kind in the next months. In this case, also we have a quite flexible range of flow available from 5 to 3 with the small scale machine, and from 3 to up to 60 in case for the large scale machine. So now I would like to focus a bit more on our project in Finland. The project was developed by the end customer Delfort Group, that is an Austrian industrial group with several facilities around Europe, and we were required to supply a steam generating heat pump for their facility in Finland, close to Helsinki. The project was assigned to us in 2023, and the startup of the plant was done last year in at the end of the summer of 2025. So basically, the effort aimed to valorize the low temperature waste heat that was present from the production process, using let's say targeting the supply of full decarbonized steam. So we took care of the heat pump part of the project, and we developed a first of a kind solution because we proposed the combination of the heat pump and MBR system for this project. The reason behind this is that the temperature lift in this project was quite high, because the system is recovering heat from a water circuit at 17 degrees, cooling down to 8 degrees. But on the other side, the process steam, the requirement from the industrial process was to provide steam at 3.4 bar absolute with a temperature up to 170 degrees. So as you can see here, the temperature lift is quite high, and with a single compressor heat pump was not possible physically to achieve this kind of conditions of steam. So we put together a heat pump running with isobutane, so an hydrocarbon, and a steam compressor. The scope of supply of Turboden was an EPC, so we took care of all the phases of the project, from the engineering to the procurement, the supply, the installation, and the commissioning of the plant. That was carried out in the last summer, as I said before. Talking about some technical features of this system, The steam production is up to 20 tons per hour of steam. So the equivalent thermal power supplied is 12.5 megawatt at 3.4 bar absolute, as I said before. So and 170 degrees. So the steam conditions are superheated. As a heat source, as said, we are exploiting the heat content of a low temperature water loop that the nominal condition is 17 degrees, but could be, according to the design, from 30 to down to 10 from seasonal changes. The COP, so the efficiency of the system, is around 2. That is very good for a case in Finland, as Professor Arpagao said at the beginning. Here, the cost of electricity is quite low, so a COP2 is way better than compared to the gas price. So the OPEX is well improved. The working fluid, as said, is isobutane. In this case, we are using a compressor, an inline compressor with 2 cases in series with a mechanical power of 6.5 megawatt electric. As you can see on the right, you see quite well how is the layout of the system. So there is on the left, bottom left, the compressor skid with an electric motor. In the center part, there are all the heat exchangers, both the evaporator, the condenser, and the separators internally internal to the heat pump circuit. On the left, high side, let's say, of the picture, you see the steam separator, basically the steam generator that is feeding the MVR compressor. So this is the plant. It was quite challenging project because we had to fit so the plant has to be inside a building that was already present on site. So we had to manage the layout in a way that everything was fitting the rooms available. The very final slide that I want to show you here is concerning relating to the first week of operation of the plant in early September last year. And you can see quite stable production. And I would like to focus on the red square here, where we can see a specific, a peculiar condition of the steam production. Because, as said, the heat pump is feeding directly the industrial process, so the production of the paper in the facility, and so it's subject also to fluctuations related to this industrial process. In this case, in this square, you can see that there is a sudden decrease of steam production that was required by the user, so the industrial process itself, because during the paper production there could be a paper sheet break, so the paper machine breaks the paper and has to be stopped. In this case, of course, the steam heat pump receives a request to reduce suddenly the production of steam that you can see better on the bottom left of the picture, because one of the paper machines were stopped. In this case, the thermal production, that is the black line, was required to be reduced from the nominal power 12.5 megawatt to the partial load condition at 9 megawatt. So one of the paper machine were stopped, and we had to adapt the steam production. You can see here that this was done quite quickly. In few minutes, the unit was able to adapt to this request, keeping basically the COP constant, because the red line is the COP. So also you can see here that also on partial load conditions, the heat pump and the MVR are able to provide the nominal efficiency also in these cases. In the last two lines here, you see the mechanical, the electrical, or actually the electrical consumption of the two compressors. The first is the heat pump compressor. The second is a steam compressor that also were adapting very quickly. On the last part of this period, let's say of stop of one of the paper machines, you see that also when the paper machine was started up again, the request from the customer was to supply again the nominal steam value. And also here, the heat pump was able to go to the max load in less than 20 minutes. So it was 15 minutes approximately. So in a few minutes, you see that also we can adapt very quickly to the steam demand. So yeah, this is my last slide. I hope that my explanation was enough clear and interesting for you to understand what we did in Finland for our first project for steam generation through a heat pump. Thank you for the attention.
Thank you very much. Thank you very much, Rocco. Sorry, we are in the same room. Thank you very much. You can all hear me now, I hope. Let me know if not. So thank you. Let's move to the Q&A. We have some minutes left for that. I think it was very interesting to hear both this business model tool from Cordin Arpagaus and then the different cases in the paper and pulp sector. I'm just trying to shift. Yes. Okay. So we had some questions in the chat. So we had the first question from Quentin Audouy for Cordin Arpagaus on the tool and on the electricity to gas price ratio, so that you indeed reflect that in the tool, and questioning whether it's also interesting to integrate the LCOE in the tool. Is that foreseen or not?
Very good question, and very important to have the levelized cost of heat or of energy over the whole lifetime of the heat pump. So typically over a lifetime of 20 years or so for business calculations. What is needed is to have more information on the capex, so on the installation costs and all that. And here we can just rely on fit functions or some data from the demo cases in push to heat. So for sure, this is intended to be included. Abdel showed it for some demo cases already for the replication studies. And honestly, we had a lot of discussion about these values, about the costs. So it's not so easy to come up with a reliable cost, because we need really data from realized examples. Maybe Turboden can share some real costs that they faced on that, and what was their, let's say, levelized cost of heat in their paper factory for this heat pump integration. That would be the best, let's say, best guess.
Thank you.
Yeah, I don't have now the numbers. Sorry, but yeah, it's something we calculated, and yeah, it's an interesting value.
Okay, let's see, maybe afterwards we can exchange further. I also wanted to ask, it was not in the chat, but on the tool, I think it's super interesting and really needed. Also, you see, when talking to end users, often, okay, we do not know where to start or which type of heat pump or which manufacturer fits best with our needs. So I think that will also help there. But when will it be available, and where? I suppose it will be publicly available. Could you explain a bit more about that?
So this tool development is part of work package 5 of push to heat project. This work package goes to the end of the project, so the deliverables are all determined by end of the project, which will be, I think, September next year. So this tool will be part of that work as well. If it will be public, that I'm not sure yet, because originally it was not for the public, but I think it will be very useful. So we have to reconsider.
Yeah, for sure. Okay, super good. So then we had a question from Zoran Stajik on why a fast start of such a heat pump is important. Because we're talking about big system with significant inertia, and so why do we need fast starts?
Yeah, very good question. I mean, it is really depending on the application, on the sector. Now we have seen the pulp and paper sector. They did tests to, let's say, to validate this machine in operation, and they do this start and stop tests. So this 15 minutes start and stop time is quite short for such a large machine, and this is a competitive advantage. I think flexibility of heat pumps is in as such a very interesting feature. So also for all kind of heat pump integrations, you can think about the electricity price that is fluctuating during the day. Sometimes it's very cheap, so it's better to run the heat pump at very low electricity prices to generate heat almost for free. So it's very important to have this flexibility, and this is time depending. And if the heat pump can react more quickly, then it's a competitive advantage. And with this compressor technology, I was always talking about vapor compressors, but Laura showed also the absorption heat transformer and the thermal driven. But for the electrical driven heat pumps, the compressors have a variable speed drive, or they can be turned on quickly, or and so on. I think this is a very important point, and that's why startup and stop down and so on, full load, part load operation in short time is important.
Okay, thank you. Then we have a question for Abdel. So it's a question by Michel Baugan, and he's asking on the installation and integration factor of 1.5 means that we need to consider an additional 450 euros per kilowatt for integration.
Yes, correctly. This is correct. As you have seen in the presentation of Rocco, the last presentation of actual case in also in the paper industry, there is big challenges to integrate these machines, big machines in industry. And usually the integration and the installation factor we have estimated, it could be also more than 1.5. It could be the double of the specific capex or the capex of the technology. So yes, we added 50% more the capex to include this, the integration. For example, the piping, maybe in some industries you can build a new building, for example, or to cover this new technology or new piping system, or you can do infrastructure. So yes, it's very challenging. In majority of these cases, it's not a plug and play. It's a tailored process. So we put this into consideration.
Indeed, thank you. Yeah, we often hear even from some people. I heard that the system cost is only 20% and the integration is 80%. Exactly. So that's a bit a different value. But yeah, just to show a bit the range
the scale. Yes.
Yeah, exactly, the scale.
The scale.
Thank you. Then we have a question by Ole Wollert about refrigerants. So, or not really refrigerants, but is it possible to use a water vapor air mixture as a waste heat source for a heat pump to generate fresh steam, even if the original water vapor is not directly recovered, but only utilized energetically? This seems very technical, so I would think that maybe Professor Arpagaus can reply, or it was related to the presentation of Rocco. I don't know when it was. Yeah, well, whoever would like to pick up this.
Professor Arpagaus can start if he wants.
Okay.
But
by the way, I'm not a professor.
Short answer is yes. Sorry. Okay.
Thanks, but would be nice now. Maybe Rocco can answer better than me, because you have this vapor air conditions in the paper factories.
Yes, okay, thank you. And I can confirm that, yes, it's one of the possibilities. It's in most cases, it's most of the project we are discussing currently with some customers. The humid air, so the vapor content of air, especially from drying processes, is a good heat source. So yes, the answer is yes. It needs, of course, a specific system to condensate this water content, let's say in the air. But yeah, the answer is it can be used as a heat source.
Okay, thank you. And then the last one is also for you, Rocco. So how are the isobutane leakages managed from DGS venting? Apologies, I do not know this acronym, of the compressor of the heat pumps in Delfort. Are they reintegrated in the loop?
Yeah, okay. So this is very technical. I will try to give an answer. But yes, basically we can divide the venting into two parts. The primary vent is basically only isobutane. It is reintegrated directly in the evaporator side of the heat pump, whereas the secondary vent is made by nitrogen and a small portion of isobutane. In this case, this mixture is sent to a recovery system that has an efficiency of almost 100%, is 19.9 something. So basically, almost all the isobutane is recovered also here, and to the atmosphere is going only nitrogen, basically. We expect is the first, let's say, 8 months of operation, we observe a very, very low leakage of isobutane in terms of few kilograms per year. So considering that in the plant there are several tons, it's a very small leakage that is controlled by this system.
Okay, thank you very much. Then I think we reached the end of the Q&A and almost the end of the webinar, so I hand back to Paola.
Yes. Thank you very much for everyone, to the presenter, and for everyone to stay with us until the end. If you want to know more about the project, you can scan this QR code or also look through the website, follow us on LinkedIn. There we will be published all the latest developments as well as the reports and, for example, the tools of coordinating when it will be available. Also, don't forget to follow EHPA to always be updated with the next initiatives, events, and opportunities within the association. And yes, for all the attendees, all the registration of the webinar and the slides will be sent in a follow-up email. And that's it. Thank you, everyone, who have joined, and see you soon.